Welcome everyone. Today I will discuss about a topic of matrix. Topic is symmetric and skew symmetric matrix. It is most important topics to the modified syllabus of CBSE. You should memorize the definitions and the theorem based on symmetric and skew symmetric matrix, because you have to answer multiple choice questions for this chapter. Now, to answer multiple choice questions, you need idea about theory and theorems also. Theory, theorems and properties. So, let us discuss symmetric and skew symmetric matrix. So, symmetric. So, A equals to, suppose, A11, A12, A13, A21, A22, A23, A31, A32, A33. This is a matrix, you know, third order matrix. It is written in short as Aij, then third bracket or first bracket, 3 into 3. This is 3 into 3 order matrix, square matrix. Aij, in short, Aij into this. You should cautious about symbol. Do not use this symbol. So this is determinant symbol. You may use first bracket also. So A equals to Aij. This is alternative symbol. But do not put this symbol. All of you know it. So this is wrong. This is determinant symbol. So a square matrix, capital A, is said to be symmetric. Symmetric. All of you know it. Symmetric if A equals to A transpose. Transpose matrix obtained by interchanging rows into columns. A equals to A transpose. That is, Aij equals to Aji. Aij equals to Aji. So, if A equals to A transpose, or you can write Aij equals to Aji. And skew symmetric. Symmetric if A equals to minus A transpose, or Aij equals to minus Aji. So this is alternative definition. I am discussing later A equals to minus A transpose. So consider a matrix. Suppose A equals to AAG, HBF, GFC. So this is A. So what is A transpose? Changing rows into columns. So first row will be AAG, then HBF, then GFC. Now A and A transpose are same. Here A equals to A transpose. So this is example of symmetric matrix. So A equals to A transpose, it is clear. Now look, Aij equals to Aji. This alternative definitions. So this is A12 equals to H. A first row, second column. This is A21. Look, A13 equals to G equals to A31. This equals to this. This equals to this. And this is A23 equals to F equals to A3. Look. This is diagonal. So if you change, this is A11. If you change A11, then it will be A11. So that is why no no change here. So a matrix, square matrix, definitely it's said to be symmetric if A equals to A transpose, that is Aij equals to Aji, and skew symmetric if A equals to minus A transpose. So for the second one, skew symmetric. So suppose AHG, for the previous one, AHG. So this will be minus H and this will be minus G. And diagonal will be 0. I will prove it why diagonal elements are 0. If it is F, then it is minus F. Skew symmetric. Look. A12 minus A21, 13 minus 31, 23 minus 3. This is skew symmetric. So first one, give an example of symmetric, skew symmetric example. So these are examples. You can form thousands of examples using these definitions. So A12 equals to A21. A13 equals to A31, A23 equals to A32. Now, why the diagonal elements are 0 for skew symmetric matrix? So, theorem. Diagonal elements of skew symmetric matrix are all 0. So are all 0. So prove. Let A equals to Aij, n into n, be a skew symmetric matrix. We use alternative definitions. Therefore, Aij equals to minus Agi from definition of skew symmetric matrix. So putting j equals to I. So we are getting Aii equals to minus Aii. So 2Aii equals to 0 implies Aii equals to 0. So Aii, this one is diagonal, only one diagonal, I equals to j. Elements for which I equals to j, they are diagonal elements. So putting I equals to 1, A11, 0, I equals to 2, A22, ANN equals to 0. So A11, A22, ANN equals to 0. They are diagonal elements, I equals to j. Therefore, diagonal elements of skew symmetric matrix are all 0. So this is theorem. That is why we are taking diagonal elements as 0. Then you must remember the statement theorem. Let A is a square matrix. Square matrix. Then A plus A is symmetric and A minus AT. T for transpose. You can use dashed or bar also. Is skew symmetric. Symmetric matrix. A is any square matrix. A plus A transpose is symmetric. So very simple. Let B equals to A plus A transpose. So what is B transpose? A plus A transpose, then total, taking transpose. Then from well-known theorem of transpose of first element, transpose of second element. Now this is A transpose. Transpose of transpose is original. So this is B. So B transpose equals to B. So B is symmetric. So very simple. So these simple problems are occurring in CBSE exam. For example, A plus A transpose is symmetric. Number 2, skew symmetric. Number 3, orthogonal matrix. Number D, diagonal matrix. So it is symmetric matrix. So you get pattern is changing. So for the COVID situation, questions and answers are very, very simple. That is why we have to remember these simple results. Now C equals to A minus A transpose. Exactly same. A transpose. So A transpose minus A transpose to transpose. So A transpose minus A. Transpose of transpose is original. So minus common. So this is minus C. C transpose equals to C. So C is skew symmetric. A very simple theorem, but most important theorem. Next theorem is most important theorem. Prove that every square matrix can be uniquely expressed as sum of symmetric and skew symmetric matrix. Every matrix can be uniquely, every square matrix can be uniquely expressed as a sum of symmetric and skew symmetric matrix. So proof. You may consult any standard book, proof are given. So let A is any square matrix. We can express A as, we can express capital A as A equals to half of A plus A transpose, half of A minus A transpose. Look, half A, okay, so A transpose cancel. Now, this is B, we suppose, and this is C. And we have already proved B is A plus A transpose. Half is constant, so what is B? B equals to half of A plus A transpose. And we have already proved that it is constant, no change. So, we have already proved this is symmetric. So, B transpose equals to B. So, B is symmetric. And C equals to half of A minus A transpose. You complete it, C transpose equals to minus C. We have already proved it. So, this is skew symmetric. So, what we are getting? So, A equals to B plus C. So, symmetric plus skew symmetric. Skew symmetric. So, there is similar like proof in case of function also. Every function can be expressed as a sum of even and odd function. Function may be even or odd, but you can express it, every function, as a sum of even and odd function. Similarly, matrix may be symmetric or skew symmetric or none, but you can express every square matrix as a sum of symmetric and skew symmetric matrix. Now for uniqueness, what is uniqueness? Uniqueness. So we have taken B and C are two symmetric and skew symmetric matrices. So if possible let A equals to P plus Q, where P is symmetric and Q is skew symmetric. So what is A transpose? A transpose equals to P plus Q transpose. So P transpose plus Q transpose. So this is P minus Q. Because P is symmetric, P transpose equals to Q, and Q is skew symmetric, Q transpose equals to minus Q. So A equals to B plus C, and this is A transpose equals to P minus Q. Now, this is P minus Q, this is 1 and this is 2. So 1 plus 2 implies 2P equals to A plus A transpose. So P equals to A plus A transpose by 2. So this is B. So similarly Q equals to A minus A transpose by 2. This is C. So we are taking P and Q are other two. P and Q are another form, symmetric plus skew symmetric. But we have proved P equals to B, Q equals to C. So we are getting same combinations. That is why it can be expressed uniquely. So we can express square matrix A unique as a sum of symmetric and skew symmetric matrix. So this is most important theorem. So probable question for 4 marks. Now it may be given in converse form also. So that is, suppose A equals to any matrix, suppose third order 2, 3, 1, 5, 4, 2, 2, 3, 5. Suppose 2, 4, 5. So A is any square matrix. So express A as sum, symmetric and skew symmetric. Skew symmetric matrix. So this is converse one, most important. Now look, A equals to, we know the theorem, A equals to half of A plus A transpose plus half of A minus A transpose. So this is 1. Now we have to calculate half of A plus A transpose and half of A minus A transpose. Now what is A transpose? So 2, 5, 2, 3, 4, 4, 1, 2, 5. This is A transpose. So A plus A transpose. Look, A plus A transpose. 2 plus 2, this is 4. 3 plus 5, this is 8. 2 plus 1, this is 3. This is 3. 5 plus 3, this is 8. 4 plus 4, 8. 4 plus 2, 6. 2 plus 1, 3. 4 plus 2, 6. And 5 plus 5, 10. So you have to calculate half of A plus A transpose. So you know, if you multiply a matrix by a constant, then you have to multiply each element by same constant. So this is 2, this is 4, this is 3 by 2. 4, 4, 3. 3 by 2, 3, 5. Now look, this is symmetric. This one, this, A turns. So this is symmetric matrix. Now we have to calculate A minus A transpose. So A minus A transpose, subtraction, 2 minus 2, 0. 3 minus 5, minus 2. 1 minus 2, minus 1. 5 minus 3, 2. 4 minus 4, 0. 2 minus 4, minus 2. 2 minus 1, 1. 4 minus 2, 2. 5 minus 5, 0. So look, diagonal is 0. This different, this. So half of A plus A turns. A minus A transpose. What is half of A minus A transpose? So divide each element by 2. So 0 minus 1 minus half. 1, 0 minus 1. Half, 1, 0. So look, diagonal element 0. This equals to opposite of this, opposite of this, opposite of this. So this is skew symmetric. So every square matrix can be expressed A as half of this plus half of this. So what is the first part? 2, 4, 3 by 2, 4, 4, 3, 3 by 2, 3, 5. This is symmetric, and skew symmetric is 0 minus 1 minus half, minus 1, 0 minus 1, half, 1, 0. So it is symmetric, and it is symmetric, and this one is skew symmetric. Skew symmetric. So every square matrix can be expressed as a sum of symmetric and skew symmetric matrix. So of application of the above theorem. Next theorem, A and B are symmetric matrices of same order, then prove that AB plus BA is symmetric and AB minus BA is skew symmetric. The most important theorem proof. Very simple proof. Since A and B are symmetric matrices, therefore A equals to A transpose, B equals to B transpose. So call it 1. Now you have to prove AB plus BA is symmetric. So AB plus BA. So call this is matrix, suppose this one is P. So we have to prove P equals to P transpose. So P transpose. So AB plus BA total transpose. So now this is AB transpose plus BA transpose. So you know A plus B transpose. Relating theory is A plus B transpose. A transpose plus B transpose. Now second theory, you know this is the result of transpose of product of matrices. So B transpose into A transpose in reverse order. So this is B transpose into A transpose and this is A transpose into B transpose. So now from 1, this is BA, B transpose equals to B and this is AB from 1. So we are getting this as P. So P transpose equals to P. So P is symmetric. P is symmetric matrix. Now in the same way, you try to prove AB minus BA is skew symmetric. Next, one more result. Prove that B transpose into A into B is symmetric if A is symmetric. So B transpose into A into B. So we call it P. So we take transpose of this. So transpose, B transpose A into B total transpose. And we know the theorem transpose in reverse order. So B transpose, A transpose, B transpose then this. Now B transpose into A transpose into B. Now if if A is symmetric, then A transpose equals to A. So what we are getting? P transpose equals to B transpose AB. So we are getting the original one. So P transpose equals to P. Therefore, P is symmetric. So if A is symmetric, then this one, B transpose AB is symmetric. Now, P second one, P equals to same, we are getting up to this. Since A is skew symmetric, A transpose equals to minus A. So we are getting B transpose into minus A into B. So minus B transpose into A into B. So minus P. P transpose equals to minus P. So P is skew symmetric. Skew symmetric. So this is the proof. Very simple proof. Now we consider two more simple results. Any positive power of a symmetric matrix is symmetric. Positive integral power. So let A be any symmetric symmetric matrix. Therefore, A transpose equals to N. So suppose B equals to A to the power N. N belongs to positive integer. So what is B transpose? B transpose equals to A to the power N total transpose. So A dot N times total transpose. So it is in reverse order. A transpose, then A transpose, then A transpose. How many times? N times. N times. So now A transpose is A. Because A transpose equals to A. So this is A to the power N. So B transpose equals to A to the power N equals to B. So B is symmetric. Very simple. You have to remember this result. So to answer MCQ type questions. Now second one, any positive integral power of a skew symmetric matrix is symmetric if power is even, and odd if power is odd, then it is skew symmetric. So same proof, let A be skew symmetric. So A transpose equals to minus A. So B equals to A to the power N. N belongs to positive. So BT, A to the power N transpose. A same type. Now this one is A transpose. So this is minus A, this is minus A, and last one is also minus A. A transpose equals to minus A. How many matrices N? A to the power N minus 1 to the power N into A to the power N. Now listen, if N is even, so this is A to the power N equals to B. N equals to even. So this is minus A to the power N minus B. N equals to 1. So if N is even, B transpose equals to B. So B is symmetric. B is symmetric if N is even. And B transpose equals to minus B. So B is skew symmetric. B is skew symmetric. Skew symmetric if N is odd. So you remember the theorems. So very simple. Now we consider a theorem, most important theorem. If A is orthogonal matrix, then determinant A equals to plus minus 1. So orthogonal. So we need definition of orthogonal matrix. So a square matrix is said to be orthogonal. Said to be orthogonal if A into A transpose equals to I. I means identity matrix. Orthogonal. So examples. So look, cos theta, sin theta, and this is minus sin theta, cos theta. This is your home task. You calculate A transpose and you verify that A into A transpose will be I. So if it is given, give an example of orthogonal matrix. So this is one example. Now we will go to the theorem. Orthogonal. So A into A transpose equals to I. So taking determinant on both sides. Determinant I. So using this theorem, determinant AB equals to determinant A into determinant B. So we can write A, and this is A transpose equals to determinant I. Now A transpose is a determinant obtained by changing rows into columns. We know changing rows into columns, if we change rows into columns, then value of the determinant does not change. So this also A. So determinant I, unit matrix, this is 1. Unit matrix I, 1, 0, 0, 1. So this is unit matrix, second order, I2. So mod I2, 1, 0, 0, 1. So this is 1. So mod A square equals to 1. So mod, that is determinant. It is actually determinant, not mod. Determinant A equals to plus minus 1. So determinant A into determinant A square. So determinant A equals to plus minus 1. So this is most important result for MCQ, for West Bengal joint also. So today, through this video, I have discussed what is symmetric and what is skew symmetric matrix, orthogonal matrix, and some most important theorem regarding symmetric and skew symmetric matrix. You must remember the statements and also proof of the theorems. So this will be useful for solving MCQ type problem. For the modified syllabus, you have to answer MCQ type problem for the unit 1. So thank you.